Chatbots that summarize internal documents or answer product queries are baseline expectations for enterprise software. But large language models have a structural constraint. They only know what they were trained on, and they have no inherent knowledge of a company's proprietary data. If an application forces a model to answer an enterprise question without fetching the exact context first, the model will confidently hallucinate an incorrect response. This illustrates retrieval augmented generation, or RAG. A retrieval layer intercepts the prompt, extracts relevant documents, and passes them to the language model. The model is entirely dependent on this initial fetch. If the retrieval returns wrong context, the model generates a wrong answer. Information retrieval has become the primary bottleneck and the core infrastructure required for functional AI. Traditional keyword search relies on exact term matching. It fails when users type conversational questions or use varied vocabulary. Conversely, modern semantic search aims to understand intent and meaning, but it consistently misses strict constraints. If a user queries a specific SKU, error code, or compliance clause, semantic matching can return conceptually similar but factually incorrect results. Solving this dichotomy requires hybrid search, an architectural standard that executes both exact match precision and semantic recall simultaneously. The retrieval engine executing this hybrid architecture for many of the world's top platforms is an open-source library called Apache Lucene. Lucene has evolved rapidly. It natively integrates traditional precision mechanisms with hardware-accelerated semantic vector search to handle complex, multidimensional queries. To see how modern AI systems fetch context at scale, we must deconstruct the Lucene retrieval pipeline and rebuild it from its first principles. Any search architecture requires a reliable baseline for precision before introducing AI complexity. Raw enterprise data, support tickets, legal PDFs, emails, is highly unstructured and heavily varied, making rapid querying impossible. This diagram outlines how Lucene handles this. Raw documents pass through an analyzer for tokenization. The system splits paragraphs and sentences into individual, searchable units. Next is normalization. The analyzer strips out punctuation, removes common stop words like the or and converts all uppercase letters to lowercase. The remaining tokens undergo stemming. Words are reduced to their linguistic roots, so a variation like running truncates directly to run. These refined tokens populate an inverted index. This is a highly optimized data structure that maps specific terms directly to the unique document IDs where they appear. Instead of scanning thousands of files sequentially, the system looks up a query term in the index and instantly jumps to the exact documents containing it. Developers have granular control over these analyzers. A legal database might avoid aggressive stemming to preserve exact phrasing, while an e-commerce platform leans into it to capture maximum product matches. The inverted index ensures absolute precision. When an application demands an exact textual match, this architecture guarantees zero ambiguity. A precise query into a massive dataset might return 10,000 candidate documents. The engine needs a mathematical method to determine which one is actually relevant to the user. Lucene evaluates and ranks exact matches using a tunable algorithm called BM25. This interface visualizes BM25, calculating a relevance score using 3 variables. The first is term frequency. If a document contains the query term multiple times, its rank increases. The second variable is inverse document frequency. If a user searches for a highly rare technical term, documents containing that specific term receive a significant ranking boost compared to documents matching common words. The final variable is length normalization. The algorithm penalizes extremely long documents so that a dense 300-page manual doesn't automatically outrank a concise, highly targeted 2-page memo. BM25 outputs a cleanly ranked top-tier list of documents using transparent math. Unlike pure machine learning models, where scoring happens inside an opaque neural network, BM25 provides clear explainability for why a specific document appeared first. This explainable ranking is essential for enterprise environments, requiring strict compliance, troubleshooting, and filtering by exact operational constraints. Exact matching has a critical limitation. It operates strictly on text overlap and cannot comprehend human meaning or synonyms. A user might submit a conversational prompt to an internal help desk, typing, can't log in, need to regain access. A keyword system will fail to retrieve the correct support guide if that document exclusively uses the phrase reset password. The concepts match, but the strings do not. Vector embeddings are used to bridge this semantic gap. An embedding model processes chunks of text and translates them into lists of numbers, mapping their conceptual meaning rather than their spelling. This 3D coordinate plane maps these numbers into a multidimensional space. The query, regain access, drops into this space and immediately gravitates toward a cluster of related concepts, like account recovery and reset password, bypassing the need for exact text overlap. Lucene natively integrates these vector fields alongside its traditional text fields to support this exact capability. Vector search captures human intent, sacrificing the absolute precision of keywords to achieve conversational recall. Because precise keywords and semantic vectors possess distinct failure states, a modern AI system must execute both retrieval methods simultaneously. This combined architecture is the hybrid RAG pipeline. This schematic traces a complex user query, like runbook for database failover, splitting down two concurrent architectural paths. Path A relies on the inverted index and BM25 to strictly filter the corpus for documents containing the exact term failover. Simultaneously, Path B uses vector search to locate conceptually related documents, even if they use entirely different phrasing, like disaster recovery. These two candidate lists converge at a re-ranker. This node scores the results against each other and orders them by overall relevance into a single unified list. The system then passes only these highly vetted, top-ranked data chunks directly to the language model to generate a final response. High-performance AI search requires this dual-engine architecture: semantic vectors to understand human intent, and exact match keywords to strictly filter operational constraints. Moving from internal mechanics to practical deployment, this Lucene-powered architecture drives highly measurable enterprise outcomes. This performance dashboard illustrates how the architecture systematically reduces model hallucinations by anchoring every generation entirely in verified, retrieved context. It increases operational specificity, allowing the AI to cite exact compliance clauses or troubleshooting steps directly from company literature. And it drastically lowers computational overhead and API costs by sending fewer, highly targeted data chunks to the language model. But achieving these metrics requires continuous tuning. Engineering teams cannot deploy this infrastructure once and hope for the best. Engineers must proactively manage the embedding lifecycle, track model versions, and systematically evaluate retrieval quality against real-world query datasets. Treating retrieval as an iteratively tuned product, rather than static background infrastructure, is what separates failed AI experiments from enterprise-grade deployments. Generative language models alone are incomplete without world-class data retrieval. Apache Lucene provides the flexibility and open-source control needed to avoid vendor lock-in, while maintaining absolute transparency over scoring methodologies. Building a production-ready system requires moving beyond the limitations of isolated keyword or vector storage. Fusing both of these distinct methods creates the incredibly fast, highly explainable, hybrid retrieval engine absolutely necessary for today's intelligent applications.